Hello and welcome to the Methods of Surface Analysis online video course. We are now starting a new theme, which is X-ray photoelectron spectroscopy. We've already dealt with X-rays and the EDS method, but this is another one. It works in a different way. This method holds inside two Nobel Prizes. First, the photoelectric effect was discovered in 1887. Then in 1905, Einstein explained the photoelectric effect and got the Nobel Prize for that. Then the theory of X-ray photoelectron spectroscopy method was developed by Rutherford, and the first X-ray photoelectron spectra were obtained somewhere in 1920s. And then the method was fully developed by Ziegbahn, and in 1954 he got the Nobel Prize for that as well. So two Nobel Prizes inside one method. And since then it is being developed and widely used in surface analysis techniques. So let's move on and get to know how it works. It's quite simple. If you have X-ray photons irradiating the sample, and if the photons have enough energy to knock off the electrons from energy levels of an atom and send them into the vacuum. So they must have the energy higher than the binding energy of the electrons in an atom. So if the X-rays could ionize some atoms, these electrons would fly off the sample into the vacuum. We could catch them and measure their energy. And this energy will hold the information about two things: about the energy of the primary X-ray irradiation, which we may know if we know the source, and it will hold the information about the binding energy of that particular electron. If we know the energy of the X-ray radiation, if it's monochromatic, we know the energy, we could mathematically calculate the energy, the binding energy of that electron. So by measuring the spectra of the photoelectrons, that's how they call the photoelectrons, by measuring the spectra of the photoelectrons, we get sharp peaks corresponding to specific electrons from particular levels of particular atoms, which could be calculated. By measuring these peaks energies, we could get the information about the atomic structure, we could get the information which kind of atom that was, and even which kind of chemical substance that was. So once again, how that works. In this scheme, already familiar, we have the level structure of an atom. We have the X-ray having the sufficient energy to ionize the atom, to knock off some of the core electrons of its positions. Some of the core electrons may be knocked off by an X-ray photon. So they are emitted into the vacuum. They travel somewhere through the vacuum chamber of the device, and they get captured by the analyzer. There they will get some more energy because they fall into the ionizer detector. They will obtain the energy of the working function of the ionizer. If you calculate all that mathematically, you will get the result that the energy of the electrons detected in the detector depends only on the X-ray photon energy, binding energy, and working function of the analyzer. We know two sections of this equation. We know the primary X-ray radiation energy, the X-ray photon energy. We know the working function of the detector because we know the material it's made of, but we don't know the binding energy. And we will calculate it mathematically. It's purely school mathematics by subtraction and so on. So we are measuring the energy of the photoelectron. We know the energy of the X-ray photon. We could calculate the binding energy. And thus we will know the level structure of the atom. We will look at the table and we will know which kind of atom it is. It's that simple. So the structure of the device is literally that simple. We need a source, an X-ray source, monochromatic. It's very important. It must be as monochromatic as possible so that we know the energy of the X-ray photons. We must have some kind of a sample stage where we have our sample, we could position it Obviously, it must be in a deep vacuum, ultra-high vacuum, so that the electrons could fly off the sample. And we need some kind of energy analyzer for the electrons. And that's it. These are three main components of an XPS device. It's quite strange, but in all analyzing techniques, the labeling of the electron levels is different. We already know that from the Auger electron spectroscopy, the labeling of the Auger electrons. We know that from the EDS method, labeling of the lines. And the XPS, we also have the different kind of labeling, which goes for the energy levels. For example, as shown in this table, the electrons are labeled like 1s, 2s, 2p, and so on. We all know these energies for any kind of atom. It could be calculated. So all binding energy for all atoms are already known. So that's why we could say that by measuring the photoelectron energy, if this atom or that or another. In this table graph, we have the graphs of the binding energy of various levels for different elements. On the x-axis, you have the Z, and on the y-axis, you have the binding energy. For example, for the most core electron, the 1s electron, binding energies increase sharply. As we pass Z of around 10, you already have binding energies in the order of almost 1 keV. And then we'll increase even more. For Z about 2040, you will have tens of keVs of binding energy. So with an X-ray photons having energies around several keVs, you will not be able to ionize these core electrons because it's not enough energy for that. But luckily, there are another electrons from higher levels. For example, level 3, 3s, 3p, 3d. For the Z around 40, you get binding energies there around 300 to 600 eV, which is okay. If you have an X-ray photons having several keV energies, you will certainly ionize these electrons. You will get photoelectrons, you will measure their energy, subtract the energy of an X-ray photon, and you will get the binding energy. And you will get to know which kind of atom it is. So you need an X-ray source, monochromatic X-ray source. We already know how this might be obtained. Monochromatic X-ray lines occur when a characteristic X-ray irradiation is induced. We know that from the EDS method, because a characteristic X-ray irradiation is almost monochromatic. It corresponds to the certain energy levels. You must remember those peak structures. So we can look at the peaks from different elements. We can look at their width, at their number, and so on. And we must also concern the energy of the peaks. We want it to be higher so that more electrons could be ionized with that photons. And it turns out that there are two most favorable atoms that will emit high energy and monochromatic characteristics X-ray radiation. These are aluminum and magnesium. Mostly aluminum cathodes are used. They have energy of the K-alpha line of about 1.5 keV, and it's very narrow. That's the greatest feature of that. Actually, there are two lines there, but K-alpha 1 and 2, but they are so close together, they are not resolved most of the time. And width is about 1 AV. So this is the material of which the cathode of the X-ray source is made, aluminum, most of the time. It is bombarded by an electron beam. It emits characteristics X-ray radiation, one line, very narrow, and we use that to ionize atoms in the sample. So this is an X-ray source. And the sample is, some electrons in the sample are ionized. They go off the sample, fly into the vacuum. We must capture them and direct them to the analyzer. Sometimes, even this narrow K-alpha line from the aluminum is not enough. Sometimes you need even more monochromatic beam. That's when diffraction effects come handy, and special crystals, banded crystals, are used to diffract the X-ray beam and virtually cut off the section of the spectrum. You will lose in intensity of an X-ray beam, certainly, by a factor of 10 or so, but thus you can make the best monochromatic beam possible. Sometimes it's used. Well, these photoelectrons, they have quite low energies, and they are emitted from a very thin layer of the sample. Usually it's several or maybe 10 nanometers. So the analyzing layer you are analyzing with your X-ray beam, the area, the thickness from which these electrons are emitted, photoelectrons, is about most of the time several nanometers. That's why the method is very sensitive to surface contamination. If the surface is contaminated more than 10 nanometers, you won't see the sample at all. You will see only the contaminants. And I'm talking about oxides, for example. So the surface must be as clean as possible. You must have ultra-high vacuum so that the surface is not contaminated while it's inside the machine. So you need ultra-high vacuum conditions, very clean surfaces, and then you could observe the composition of the topmost several nanometers by using the XPS method. So now the electrons are emitted into the vacuum. We must capture them and direct them to the detector. There are several kinds of detectors used, and you are familiar with the first one, the axial geometry detector, which is used in the Photoelectron Spectroscopy method. Because it's the same thing, we need to analyze the energy of the electrons going out the sample. Well, it's quite complex, but it has high sensitivity because the angle at which you are collecting electrons is quite high. Sometimes plain electrostatic analyzers are used. This is the plain structure having an angle of 127 degrees. It also can focus the electron beam and analyze its energy by varying the field between these electrodes. But most widely, hemispherical analyzers are used because they have both advantages of these both detectors. They have good resolution and good collecting angle of the collecting area. So you can collect most of the electrons, divert them to the analyzer, and analyze their energies by varying the fields between these two electrodes. So you are scanning along the spectrum, allowing electrons of certain energies to pass through the detector. That's how you obtain the spectrum. So the basic device scheme as it is, an X-ray source, sample, electron capturing stage, and analyzer. That's it. If you want a even more monochromatic beam, you add up the monochromator stage, that banded crystal which diffracts the X-ray beam. That's it. That's how the actual device looks like. That spherical port is the hemispherical analyzer, and all others are auxiliary systems, guns, and so on. But the main components are the source, the sample, and an analyzer, and that's it.